So the last time we met, we looked at this data set and ran this pooled OLS. Now, who can tell me what is it about pooled OLS that is different from OLS? What is it about the pooled OLS that makes it different from the ordinary least squares?
I'm assuming the OLS, the pool OLS has to do with the panel data.
Okay. So what makes it unique? What makes it better than the ordinary OLS?
I think that the nature of the data sets of observations over the parameters, the variables.
Instead of
instead of just data set at one point in time, taking it over the variables and over the observations.
okay. So one thing about the pooled OLS is that it increases the sample size. So instead of having one sample or one observation in one period, you are having that same observation in multiple periods. So you are able to look at a particular organization or individual factor, that same thing at different periods. And because it's the same thing, people would think it's the same thing, but then the pooled will help you to know that it's the same thing, but it's changing in forms over time. And that is why unique thing about a pooled OLS. But the way you estimate it is the same as the way you estimate the normal OLS. So because it is pooled, it is solving some problems. And one of the problems it's solving is the issues of multicollinearity. Because when the sample size is small, you are likely to run through multicollinearity than if they are large. Because the multicollinearity will dissipate, will vanish with more samples. So that is one thing. The other thing is that issues about heteroscedasticity will not be pronounced because it's there all right, but it's not going to be that big. Serial correlation and several other things. So that is the pooled OLS. It doesn't mean that those things are not there. In fact, they are there, but they have to be corrected. And they are easily corrected. All right, so if you look at this result, the first question we want to address is, the question is, which independent variable has the largest coefficient and why? Now let's interpret that. So which independent variable has the largest coefficient? Remember that if you can remember the specification, wage was logged.
Yes.
So it's not just nominal wage, but we are dealing more with a real wage. And therefore the interpretation will be percentages. So let's go back here. And then which independent variable has the largest coefficient? And how would you interpret that? Let's deal with the first one. Which one?
Largest coefficient. I see union.
Yeah, 18%.
Good. Now, union has to do with whether a person is belonging to a union or does not belong to a union. So you are talking about a unionized worker versus a non-unionized worker. So the union here means someone who is a unionized worker. So how would you now interpret this? By the way, anytime you're interpreting, check the level of significance so that you will now conclude that it is significant or it's not. Now, looking at the 3 stars, is significant at what percent?
At 0.1%.
Good. 0.1%. That's it. Now, how will you interpret the union? Of course, you should start with on average, and you should start with a 1% increase in this.
Okay, I was thinking on the average, when a person is part of a union, the log of wages is expected to increase.
You cannot use the log of wages here because you are using percentage.
Yes, so the percentage wage would increase by 18% if we were in a union than if we were not in a union. Or other variables constant.
Yeah. So a unionized worker is more likely to have 18% more wages than a non-unionized worker. All things being equal, on average. No. That is the idea behind this. And this is not just a statement out of the blue. This is significant statement that we are making. So that is how you interpret it. So the write-up here is that, on average, holding all other factors constant, that is the ceteris paribus, unionized workers earn 18% more than non-unionized workers. Let's go to the estimate of return to education. What is the estimate of return to education?
Education is 0.09.
Okay. How would you interpret that? Remember, this is not
A dummy.
Yeah. So how would you interpret? Sorry?
Please come again. You said this was not
a dummy variable.
Okay.
It's not a dummy variable. It's a varying regressor. It's a varying regressor.
So on the average, a percentage increase in education will lead to a 9% increase in wages. Holding all other variables constant.
And is this significant at what percent?
That's still 0.1.
Okay.
Yes.
So that's it. So if you should raise education by 1%, salary or wage will rise by 9.1% at a 0.1% level of skill. So it's important to know how you interpret the thing when it is logged. Remember that we are not interpreting it using the log. We are not saying the log of wage will increase by, no. It is a log that is making us use the percentage.
Okay.
So we have to now not deal with a log of wage, but just the wage. All right. Let's go to the marital status gap. So this is the marital status gap.
Okay.
Remember that this was sorry?
Okay, look, I was trying to explain it, interpret it.
Okay, go ahead.
Okay, so for the marital status, you are saying that on average, holding all other things constant, there's going to be an increase of 10.8% in wages for when, and then it's also significant at 0.1%.
Okay. You were a bit close. There are some two keywords that you brought shouldn't have come. And there was one keyword you didn't bring that should have come. So you said that a 1% increase in marriage. But the thing is that marriage is, sorry?
A unit, okay.
If you
I
try
don't
to
think a
defend
unit
it, you mess it up rather.
Okay.
So that a married man is more likely to receive a 10.8% increase in wages than a non-married man on the average, holding all other things.
Again, no. You see, that increase here, because it's not changing, we cannot be using the word increasing.
Okay.
Correct. But you rather would say that the wage of a married person, of course, given all other factors constant and all of that, the wage of a married person is 10.8% more than the wage of an unmarried person.
Like, is it absolute? So I thought this was more like a prediction.
It is a percentage, but it's a 10.8% or approximately 11% more. So it's not like it's increasing, but it is already. So the wage is already there. That the married person, is above, the married person's wage is above that of the married person. Not that the wage of the married person is increasing than that of the married person. So the point I'm trying to say is that this is a fixed variable, and because it's a fixed variable, the interpretation is on the wage, not on the marriage.
Okay.
So the wage is not increasing.
Okay.
The wage is not increasing for the married person. The wage is more for the married person than for the unmarried. But for education, you can say that education is increasing by 9.1%. Okay. But we cannot say that, for education, we can say that the wage is increasing.
Yes.
If education increases. And for here, we are not saying the wage is increasing. No, the wage is 11% more.
But Doc, then how do you determine the fixed ones?
Oh, they are all the dummy variables.
Okay, so all dummy variables are fixed.
Correct. Within the specified period.
Okay.
Things like ethnicity, anything on ethnicity is a dummy variable. Education, experience, they are all dynamic variable. They are not dummy, they are not static. But the static variables are married. That's why they've given you yes or no in the data. In fact, they are usually English words. They are letters other than numbers. Even if they are numbers, they are dummy variable number, binary, 0 or 1, like the time. If you look at the time to their time, but they are time, but they are dummies. We call them time dummies. So that the day, the 1981, the 1982, 1983, all of these are dummies. They are time dummies. So the way you interpret a static variable, that is an unchanging variable, is that you got to interpret it as the dependent variable is or is not. Because you are either married or you are not married. Not that you are increasing from non-married to married. No, it's not increasing. You are either a Hispanic or a Black. It states what it is. You are not increasing from Hispanic to Black. And so the wage too is not supposed to be said to be increasing or has increased. Because That will make it a changing variable. But that the wage is, is predicted to be, in this case, 11% more for a married person than for a single person. Yeah, it's very important you recognize this. So this is a point here, that on average, all other factors fixed, a married person earn about 10.8% more than an unmarried person. And we know that is significant at 0.1%.
Yeah.
Godwin is clear, right?
Very clear. That.
Super. Let's go to the next one. This one is tricky, but we'll get it. You have an open mind. You don't copy. You'll be fine. What do you make of the estimate of the 1987 dummy variable? Remember I spoke, you see, the 1987 is a dummy, like we said. So this is a 1987 dummy variable. Look at it. Now, it started from 1981. And then, if you look at the value carefully, as you move from 1981 to 87, what is happening to the coefficient?
It's increasing.
It's increasing. Now, this is time dummy. It is there to indicate how wage is changing over this 8-year period, over time. How is wage changing over time? And you will notice, what do you notice, by the way? Let me ask you, what do you notice? By the 1987, what do you notice?
Well, I think beyond the coefficients increasing, to the significance also increase, so from 5% or 10% to 5% to 1% to 0.1%.
Good. But let's go to the first point. You say apart from the coefficient increasing. So what does that mean in terms of apart from the coefficient increase? What does that mean? If you
Means year on year. It means year on year, the
Wage is increasing.
exactly. Over what?
Doc, over time.
Over time. So over time, wage is increasing. So if a person gets to that labor market, that company, remember these were 545 working employees, young men between the ages of 17 and 23. So when you enter the market, you are saying that your salary is low or your wage is low. Normally, when you do that, company managers will tell you that, hang on, it will be increasing with time. It will be increasing. So you notice that by the 87, when you entered in 1981, by 1987, your wage has increased by how many percentage points?
17.3 percentage points.
Exactly. It has increased by 17.4. Okay. So that is one of the things that we observed when it comes to the wage. And then the point you made is also very significant, that the significant level is increasing.
Yeah.
It's increasing. That is why people like their wages, because they know that, oh, I just started. But sometimes if you don't take this day and age, you'll be waiting for 30 years. Yeah. Okay, so this is the point. The positive and significant value, 17.4, implies that all things being equal, nominal wages has grown by 17.4% over the 8-year period. Now, why do you think, and this is important, that is talking about nominal wages when we use the log? Even though we are using the log of the wage, why do you think we are still talking about nominal wages and not real wages? This one is it's a tough one. because the log is not for the real or nominal. It is for the interpretation, the percentage. Secondly, because this is not a particular independent variable. This is an independent variable with time. Thirdly, real wages are not changing by themselves. It is nominal wage that is changing by itself. Okay, because the real wage is actually the purchasing power, and that purchasing power is increasing not because the wage itself has increased, but because of the economy-wide situation. So even if I increase your nominal wage, okay, and the inflation is still bad, you will still, the real wage can still be constant, isn't it?
Yeah.
Exactly. So your wage has gone up, but inflation has also gone up. So you are back to square one. So that's why we cannot talk about the real wage. The real wage can be constant, but the nominal wage is what is increasing. The nominal wage is what the company managers will have to touch, but they can't control the real wage because they can't control inflation. And that's why this is on nominal wage.
It gave two other reasons. One was that the real wages are not changing by themselves. The nominal wages that are changing. Then it gives some other reason.
Yes, I said that.
What was that? The log was for the percentage.
Percentage.
The log was not meant for the whether it's a real wage or nominal wage. The log is introducing the percentage. Of course, it handles issues related to, inflation or non-linearity. But it is for the interpretation of the independent variables and not to determine whether it's real or it's not real. So that's the first thing. And then the other thing I mentioned is that the real wage itself can be changing by two factors, not only by the nominal wage. It is both the nominal wage and inflation. So if nominal wage changes and inflation changes, all in the same direction by the same proportion, then the real wage is static every year. I think I mentioned another thing, but I've forgotten what I said. Oh, that's all. Emily, you remember the only one?
Yes, Doc.
Okay, let's move on. So the next thing is the interpretation of experience. Let's go to experience. How would you interpret experience? Look at experience carefully. Round it to 2 decimal centers.
Okay, so that that would be 7%.
Yeah, let's make it 7%.
Okay, so for on average, holding on. Okay, an increase in experience leads to a 7% increase in the wage.
Okay.
And it's 0.1% significant.
Good. So a 1% increase in experience significantly raises the wage by 6.7%. Or in your case, 7%. So what does that mean? What does that tell you when it comes to practicality in this very data? It tells you that, the more experience you are having, the more your wages. So over the years, your experience will increase your wage, by that amount, by 7%. So when you enter that company, by that 8 years, your salary must have gone up by 7%. But to be honest, is that really nice? Suppose you are earning 1,000, forget about which currency it is. And by 8 years, your salary has gone up by 7%. Is that really nice? Godwin, is that something to celebrate?
I'm sorry, I didn't hear that.
You go into a company and by 8 and you are earning an income of say 1,000.
1,000,
By 8 years,
your
income has increased by 7%.
I mean I thought that 7% will be every year.
No.
Like 1 year increase.
But the data we are having is not every year data. It is 8-year period data.
Sounds of the average. Yeah, because we're trying to compare the experience beta to the dummy, the time dummies, to see the changes, whether they have anything in common.
Yeah. If you want every year, that was the one we checked.
That
was the one we checked by the time dummy. And so we recognize that your wage, this is general over the years, your wage is increasing by 17.4%, by the 8th year. But this one is talking about your experience. So your wage increasing because of your experience.
Okay.
So by the time you are 8 years in the company, just based on your experience alone, your wage is going to increase by just 70. Meanwhile, it is 1,000. It's 1,000. Your wage has just increased by 70. So it's 1,070 now. I mean, sometimes when you calculate and put it in perspective, you realize that, what am I doing? Anyway, that is the situation. Let's go to the standard errors. You see, taking care of your results like this helps, because it helps you to understand. There's a lot of stories now you can tell based on the numbers alone. But when you rush into it, you will not make much sense in it. See, somebody might think that, oh, my salary is good. Even 17% increase, if you are earning 1,000, it means that your salary has just gone up by 170. Just because they are pitying you because of inflation, or just because of inflation. All right. Let's go to the standard errors. Now, if you look at the standard errors here, the standard errors, the estimate divided by the standard errors is what gives the t value. The estimate divided by the standard error will give you the t statistic. Then from the t statistic, you're able to generate the probability value, which is the last one. And then you can use the probability to find the confidence interval. So these steps, know it. Question is, these standard errors, are they correct? Are they correct? And why do you say yes or no? Are they correct? The standard errors. But there's a simple reason why they are or why they are not.
I'm not sure, but because they look very small, I could say they are correct.
Okay. Emily, you should also get some. Let's see. Are they correct? The answer is no. Why not? Because we are using pooled OLS. And because we are using pooled OLS has some issues. And those issues will be affected by these standard errors. So one of them is this. There is an unobserved heterogeneity. There is an unobserved individual specific effect. In this case, worker. A particular worker may have a unique skill. That skill is what is defining the worker's experience. But you have calculated the experience of the worker. You recorded the experience of the worker. But that hidden, latent factor, like maybe the person has unique programming skills, unique ability, but it's hidden. So you don't see, you don't capture it. And that will be influencing the independent variable. In influencing the dependent variable.
Or is it automatic that always the standard errors of the post OLS would not capture the?
Oh, yeah. They are flawed. Always. Always. It's because of the way the pooling is done. And so when there are hidden factors, you got to take care of those hidden factors. Because the thing is that over the years, someone experience is increasing, another person's experience will be more than another person's experience. Do you agree with that?
Yeah.
Yeah. But then if you measure experience by years, which is what we are measuring it, okay? We are measuring experience by years. Then in reality, everybody has increased his experience. Suppose we all enter the market at the same age, at the same time. By 8 years, we all have 8 years experience, isn't it?
Yes.
So how come somebody becomes better than another and one goes to managerial position, the other does not go to managerial position? There are some latent factors. There are some factors that are unseen in the data, influencing the skills, the experience, the acumen, the technical know-how of the person, which warrants the person to be part of the board and another not. So if those factors are there and they are embedded in the error term, because remember, the error term was not composed. With the pooled OLS, the error term doesn't contain anything. It doesn't contain individual specific effect. It doesn't contain time specific dummies. It is just a noise. It's just a noisy term. So the errors across this time period for each worker, if these errors, and they are usually, if they are positively correlated with the independent variable, that will invalidate, it will nullify the standard errors. The standard errors are likely to be big. And by the way, you don't want the standard errors to be big. Why not? Watch it here. Watch it here. If these standard errors are big, if you divide the estimate by the standard errors, then the t-value will be small. Do you agree with that?
Yes.
And when t-values are small, remember t-statistic. The conclusion in hypothesis testing is that the test statistic should be greater than the critical value. So if the test statistics are going to be smaller, they are likely not to be greater than the critical value.
Okay.
For you to reject the null hypothesis of
Okay.
insignificant estimate. And to support the alternative hypothesis of significant estimate. And so you will have no choice than to, if the standard errors are big, you will not have significant estimates relatively. And then your p-values are likely to be also small. Now, in this very example, the estimates are significant. Majority of them are significant. But it does not warrant that the standard errors are not invalidated. The thing is that, how would you know or not know whether the standard errors are bad? Because right now, your estimates are significant. So you might think that they are not bad after all. But unless you try to correct for the standard errors to see. Okay. So let's go back here. So we know theoretically that the standard errors are invalidated. And so your interpretation will be flawed. We're going to give you an example here. If a particular ability of a Hispanic worker differ from other Hispanic workers, And if the innate quality is not captured by education, so your education should capture the skill, the innate ability, the unique ability of an individual. Experience doesn't also capture. The OLS estimator will be biased. Why will it be biased? Because normally when you collect a panel data, the panel data that you are collecting is the error, the individual specific effect is allowed to be correlated with the independent variable. But you want that latent ability, which is the individual specific effect, the UI. You want that UI, which is affecting the wage, because the person's wage is increasing because of his experience, but then it's not, experience is nothing, it's doing nothing. It is an innate ability that is making that person's experience to be seen as better than another person's experience, not the time spent. Okay, so you want that ability to be also correlated with the education and experience. So if you omit the ability, which is of course omitted in the panel, pooled OLS, okay. If you omit that ability, and yet it is correlated with the education, with the experience, and all of that, then the OLS will not be consistent. It will be inefficient. And some people think that when you pull the thing across time, it doesn't change the basic point. It changes the basic point, but it doesn't. The fact that you are pulling the thing across time doesn't mean that you are solving this unobserved heterogeneity. And it's a usual problem with OLS. So what do you do? What do you do? If you want to still use the pooled OLS, which sometimes is great, and we'll come to the test next time. If you want to still use the pooled OLS, what you do rather is run the pooled OLS, but institute a corrective measure. So and I'm going to do that very soon, institute a corrective measure. So you put it into the command, the R command, that I want it to still run the pooled OLS like you've done, but I want it to solve for serial correlation and heteroscedasticity. One way you can do that is by instituting the white test, or the white heteroscedastic autocorrelated consistent standard error. Introduce that. The problem is that it doesn't solve all the issues about pooled OLS, but we'll still do that now. It doesn't solve all the issues about pooled OLS because the other issues it doesn't deal with. So in order to do that, you invoke the library sandwich and the LM test. You can install them, load them, and let me see, I did that here. Let me see if I can show you. So we are still running the pooled OLS. Please let me know when you can see the results. Do you see the screen?
Yes, Doc, we can see the Excel file.
So I just ran this command. That is the normal coefficient. Okay, this is a pooled OLS down here.
Okay.
That's what you have there. Basic.
Hello, Doctor. I dropped briefly.
Okay. So I'm saying that if you still want to use the pooled OLS, it's fine. Just solve the standard errors in the pooled OLS. Even if you think that there's no problem with the standard errors like we have done, still correct for that using the white correction.
Okay.
So first I want to show the normal pooled OLS and its standard errors. So that's the normal pooled OLS, the one we did before. I'm replicating it here. And the standard errors are the ones there. Now, there are several ways to do the correction. One of them is called variance covariance matrix, which solves for heteroscedasticity. And it also solves for clusters, because when they are clusters, groups, that can bring about a lot of heteroscedasticity because there's a lot of heterogeneity in the process. So I run that command here. I'm highlighting it here. And I run that here. Watch it today. So this is kind of solving only heteroscedasticity. You can see that it's not even good. You realize that. The coefficients, most of them, remember the estimate will never change, but the standard errors will change. So if you look at just even education here, the standard error is 0.01. But before education, well, it's similar though. The standard error is 0.005, which is approximately 0.01. If you check the last one for the time dummy, the dummy is 17.3 or 4%, and the standard error is 0.05. Okay. The estimate will not change. In this one, it's still 17.4, but the standard error is 0.08. So you can see that the standard errors are inflating here. So you have to correct it. How do you correct it? One way, another way of correcting it is by using Arellano correction. The Arellano correction, what it does is that it estimates the robust covariance matrix for the panels. Sometimes it's called white Arellano, and handles group heterogeneity. So that is what I'm going to run here. There you go. You can see that the Arellano, I don't know if you can see, it seems to be better.
Yes, sir.
Okay, what makes you realize that it's better?
Okay, Doc, so if we take the 1987 one as an example, it's reverted back to 0.5. The previous one was 0.8, sorry, 0.08, but now it's gone back to the 0.05.
Okay, so a quick general observation you see here is what makes this, Arellano, white Arellano one better? Looking at the stars.
Okay.
Did you realize
now,
that?
Okay, the 3 stars have increased again. Yes, Doc.
Yeah. There are more significant values at, 0.1% and 1% than on the 10%. For example, if you go to the original here, look here. In the middle, there were more 10% in there.
Yeah.
But, and of course, if you look at experience is the only one that has switched. Experience was 5%. Yeah. But when you look at this thing, the experience squared is 5%.
It's 1.
Instead of 1%. It was 1% before. But you can see that the time dummies are all significant at 5% or less, which is good.
Yes. So
this white Arellano seems to be great. But there is one that is perfect. Perfect. And this is known as the Newer West standard error. The Newer West standard error. Now, what that one does, and this is very unique, is that it doesn't only solve or handle heteroscedasticity, but also serial correlation at the same time. So it is sometimes called heteroscedastic autocorrelated consistent standard error. It was published in 1987 and 94, and this is that command here, which I'm going to run. I decided to just call it pulse.nw, and this is in the slides. Okay. Pulse.nw. You see, if you check the command, after the variance covariance matrix, the VCOL, there's NW, which is representing the Newer West. Let's run that and see what happens. Okay, so this is it. It's supposed to be great, but it's not all too different from the pooled OLS original one, isn't it?
Yeah, it seems it's closer to the original one.
It's closer to the original one. Okay, which then goes back to prove that our original one we thought may not be the best, probably there is no big issue in the original one after all.
Yeah.
Yeah, that's what it means. But remember that we have just used different ways of handling possible unobserved heterogeneity. Now, in a normal paper, you would have to bring these solutions together. And you see this in the end. You have to bring these solutions together to handle it. Let's go back to the slides. The key point is that you got to try different means to eventually handle the possible heteroscedasticity and autocorrelation in the pooled OLS. After you've handled it and you've shown that, oh, I did this one, I ran this one, and ran this one, but the results are all the same, or the original one is better. Then you can now base on that, because you have the results shown in the table. You can now base on that and say that, oh, I am ready now to still go and use the pooled OLS. And okay. All right. So in your column, you will have one table for the pooled OLS, one table for the white Arellano, and then one table for the Newer West. One column for each one of them. You see this in the end. What is the second approach to remove the unobserved heterogeneity? Now, the first approach that we are using to remove the unobserved heterogeneity was the pooled OLS. But what is another way to remove the unobserved heterogeneity? Is the first difference method. What it does is that it eliminates this heterogeneity, which, as we know, it occurs when the UI, the individual specific factor, the latent factor you don't see, which is inside the composed error, when it is correlated with the regressor. So when the covariation is not zero, it means that it is correlated. And when it's correlated, then you have a problem of endogeneity. Endogeneity is a problem when an independent variable, look at the word, it's even supposed to be independent. When an independent variable actually is not independent because it is being influenced by a latent phenomenon, an unseen, unobserved factor before that independent variable claims to be affecting the dependent variable. That situation where that guy that claims to be independent is not even independent is a problem called endogeneity. When you have that problem, like we did, we know that the OLS, the pooled OLS will be biased and inconsistent. We know that. That is why you try to use what? The Arellano white, Arellano, or the Newer West to correct for the standard errors. Just trying to see whether the problem will be handled somehow. But the best is to use the first difference method, which removes this fixed individual specific factor by first differencing the data. And we are going to see that very soon. By taking the lag of the model, subtracting it, and then the time constant, the time fixed component, the intercept, and that of the UI are eliminated. When they are eliminated, then we can have a new model, which we can now go and use the OLS to run now. So let's take a typical example of this. This is a general panel data model here. And you have the individual specific factor there. You have the time specific factor here. You have the normal noisy idiosyncratic error. Okay. Now, this error term, as we know, will not be necessary in the specific panel model because it will enter into this UI. Okay. Now, we are going to take the first difference of this YT. So we take the lag, the previous year. So instead of YT, we subtract YT minus 1 from it. So because we've done this to the left-hand side, you got to do the same thing to all of the right-hand side. Everything in the model, we got to take it. We've got to subtract their lag from themselves. So you have the alpha here, which is a current time period. You subtract its lag from it. You have the x, which is a independent variable. You subtract its lag from it. Now, I have bracketed this one for a reason. Then you have the time dummy and then its lag as well. And then finally, you have the error term and then its lag. Okay. Now, the equation is still balanced. We go to the next thing. We can now use the delta to indicate the lag of the dependent variable and say that delta YT is the difference between the current time period and the previous time period. The same thing for the independent variable. But watch it carefully. You can see that these constants and their lag are cancelled out. Why? The reason why they are cancelled out is that, first of all, they are constant. So if you take a constant value from its constant self, okay, it's 0, more or less. And that is why you can have this. And that is how it is for even the time dummy as well. The individual specific factor is also gone because it is also sort of constant. Okay? But watch the error term. The error term cannot be out because it's not constant. Okay? It changes across individuals and changes across time. Okay? It changes across individuals and changes across time. So we cannot single that out. So the difference between that is also shown here. Now we are getting a definition of the first difference. Look at all the variables. You see that all of them are constant over time. The variables that were supposed to be constant over time were education. So in the first difference, that is assumption here. Education is constant, experience is constant, ethnicity is constant. All of these constant variables are going to be removed from the model in the first difference model because we just did that. We just did that. We just removed all of the constant variables. Okay. So what do we have in the original data? Well, you will have all of the things, but remember we have education. Education is constant, so it's no longer shown here. It's no longer shown. Experience is also said to be constant. Remember, the experience is constant because it is presumed to be determined, to be deterministically, determined in the model. It is not changing once you start the work. Your experience, okay, so education is not changing because you're not going to school within the 8 years. Experience is also, fixed because even though it's increasing by 1 percentage point for everybody. So at the end of the period, it's like we all have the same experience. So we are all affected equally. So we don't need to look at the changes. It's as though we're all not affected at all. That is first difference. Okay. And ethnicity, as for that, we know that it's already fixed. Okay. Hispanic, Black, and all of that, they're already fixed. So with that, this is our new model under the first difference approach. You see, the key point you want to know is to know how to formulate the model under each model, formulate a specific model under each generalized model. So you can see here that married is not constant. That is why it is shown here. Union is not constant. That is why it is shown here. I remember the pooled OLS, everything was there. Everything was there. The time dummies are down here. Okay, they are here because they are changing. They are changing over time. And then the error term, as it is also changing over time. So it's there. So on the basis of this, anything that is changing over time has to be the first difference. With that in mind, we go back to the pooled OLS and we go and run the model for first difference. So let me go to the R. Okay, and you can see my command here, which you also have. I just decided to call it WFD. That is a wage band for the first difference. I'm using the parallel linear model, which is a PLM. The log of the wage is still there, log wage. Education. So watch this. I am putting education there. But remember we said that education is constant, right?
Yeah.
I am putting experience there. Even though we said experience is constant. Remember that?
Yeah.
I am putting, what's the other thing that we said is constant? Experience, ethnicity.
Ethnicity.
Good. Ethnicity is also here. Now just watch what first difference is going to do. That's a beautiful thing. Everything, we're going to put them. And now we are going to run this model and show the results. What has first difference done? Look at the results here. What do you sense that it has done?
No, it has removed it.
Yeah. It has identified those constant variables and has removed them from the model. Okay. So remember, what we are doing is that we are not saying that first difference is the best. It's one of the ways to handle the unobserved heterogeneity. We are just checking whether it is able to do that. So let's see, experience square. Now, it did not remove experience square, even though it removed experience. You know why? Because even though the experience of the person is constant, the experience square of the person is not constant.
Yes.
Can you think about why? You got to be incredibly smart. The experience is constant, but experience square is not constant. The experience you came with, the experience you came with, over the year, the experience you came with, which is in the data set, is constant. That experience that you entered the market with, that experience is constant, okay, for the 8-year period. When I say it's constant, remember that for each year, there is an experience number.
Yeah.
And that experience number is what I mean by it's constant.
Okay.
But the experience changes in the data is not constant. Because as you go to subsequent year, your last year's experience has changed to this year's experience. So when you look at the value of the experience square, you go and check the experience square. Okay. If you check the data set, you will see that the experience square for each person is changing. Okay. Because your experience is naturally increasing, but it's increasing at an increasing rate. So experience can change. It can also be increasing at a decreasing rate, by the way. So in other words, the experience is not, a person can be in the company and then over time, his experience is even going down. There's no additions to the person's experience. But then the actual experience is constant though. He's not bringing any experience from outside. The experience he brought is remaining as it is. But he's supposed to increase his experience. But sometimes after 10 years, the boss will go to the person and tell the person, so you've been here for 10 years. Why? In other words, you are not adding to your experience. Anyway, so that's why experience.
Guys find it difficult to add technology. If there's an increase in technology, a new innovation, they struggle with all these things.
Exactly. That's the point. So the person has not improved the experience. But if you use years, the person will tell you that I'm getting experience, isn't it?
Yes.
Yeah.
That's the point. That's the point that we are talking about. Anyway, unfortunately, the first difference doesn't really give us much, doesn't really tell us much results significantly of the data, if you look at it carefully. So what can we say? Well, we can say that the first difference is good, but doesn't do much thing for us. So let's go to another approach to handle the unobserved heterogeneity. We are back to the slides. Now, another way to handle the unobserved heterogeneity is to introduce those UI into the model as constants. We call this least squares dummy variable. Least squares. So the time aspect allows us to estimate the individual aspects as a further beta parameter with this transpose. So this least squares dummy variable regression, it is good. It adds a potentially large number of independent variables to the basic specification. And there are a lot. There are a lot of independent variables because you're looking at it for each time period. And sometimes you even try to estimate it, and the R will tell you that it's not possible and things like that. So under the model, all you got to do is change the thing to, so you want to come here. Under the model, we use FD for the first difference. During the pooled OLS, we use pooling. Okay. Then under the model, we will use between for the one I just spoke about, the least squares dummy. We use the word between to estimate the model. We're not going to do that now. We're going to another one that is used to deal with static panel data models. Static. And this one and the next one are the most popular, the most powerful, and the most popular. Now, it doesn't mean that the pooled OLS is not good. I'm sure you can see that right now they are good. Yes. This model, this static panel model, is known as fixed effect model. Watch what it does. It basically controls for all the variables that are fixed. So the variables that are fixed, they are not included. It's just like the first difference. They are not included in the estimation process. For example, suppose you have variables like culture. Culture of a company might be so fixed in the company that you don't even know how to estimate it. It's kind of latent. Religion. At least within a year, it's called that geography. The company is located in the same place. The climate doesn't change that much. The gender doesn't change that much on average. Race, quality, ability, behavior. All of these are latent. They are unobserved. And if they are correlated with the independent variable, the OLS will be inconsistent. Full stop. So what do? What the fixed effect does is that it tries to eliminate them, because if they are there, they are going to cause inconsistent OLS estimate. So the fixed effect, which is also called within, not between, within estimator, what it does is that this individual specific factor, this UI, becomes constant because the thing is fixed. You got to make it fixed. So it makes those ones fixed. They are not changing. And then it includes rather time dummies to control for the effect. You can add the usual binary independent variables, 0, 1 independent variables, but not variables that are supposed to be fixed. Okay, it's very important to get that. Not variables that are supposed to be fixed. And we're going to see how the fixed effect model does this. So look at the general model. This is the general model. This equation 1 is the general model. The question is, how do we reformulate this model so that we get a fixed effect of it? Well, the first thing is to find the average of each variable. So we're going to find the average of the dependent variable, the average of the independent variable, the average of the UI, the average of the lambda I, the average of the epsilon IT. We're going to do that. But we are finding the average of each one by T. We are finding the average relative to time, not relative to individual. So we're going to use a bar to indicate across time. So let's go here. So we are going to take the average. Look at this one here, the average of days over time, and we'll call it Y bar. So Y bar, we'll not write the T again because we have already done the average over time, leaving us Y I bar. The X IT, if we take the average with respect to time, we also get XI bar. I hope you guys are following.
Yes, Doc.
Now we go to the epsilon. The epsilon, remember, it is relative to time. Okay, so you have the time here, and then the lambda, we take it. But remember, we didn't take the UI. Because the UI has no time. The average is being taken over time. So for this one too, we take the bar for them. Then we stop it there. Now, on the basis of that, we reintroduce these averages. So you can see that on the left-hand side, the dependent variable is now these averages. And then all these other ones, we have the averages. UI is here. We've not taken the average. So I've indicated here that the UI doesn't depend on time. So its average over time will be itself because it doesn't depend on time.
Okay.
If we take equation 1 minus equation 2, this is our equation 2. Remember, equation 2 is the one that contains the average. Equation 1 is a general model. So if you take equation 1 minus equation 2, it means that you're going to have the general model without a bar minus the yi bar. This is what you get. So this general model without a bar minus the yi bar. Everything without a bar minus the yi bar minus the xi bar. Everything without a bar minus that, minus itself. Okay. But remember, we said that this UI, it doesn't change with time. So if you do it minus itself, it also doesn't change with time. So this is where you kill it off. The unobserved heterogeneity that you've been fighting, that it is worrying you, is worrying you. Now you can eliminate this unobserved heterogeneity. And I keep that on the rest. The final thing is this. Anything that is having IT minus I and its bar, I can represent that with a star or something. Okay, or with a tilde symbol. So this first tilde symbol is the one that is on the top here. Okay. YIT with a tilde symbol on it. This second one is a transpose of the beta XIT with a symbol on it. The lambda, we have that. Remember the UI is gone. The lambda T with a tilde symbol in it because it is with time. And then finally the epsilon. This equation 3 is a fixed effect model. Remember, the UI is gone. So you can now estimate it by normal OLS and extract the beta parameter. When you do that, it is known as a fixed effect model or the within estimator model. But then the beta parameter you get is not going to be beta cap, but it's rather going to be beta W, where the W is indicating within, within effect model. And that's what we're going to do here. Of course, the other things we'll add, as always. You can always add the time dummies. And the time dummies will always be there as it is supposed to be there. As for time dummies, you always choose to add them or not to. There's something you want to conclude here before we estimate this. It is a fact that the UI was not included. Okay? So this D here is a dummy variable for the time dummies. And you, even if there are error terms, the UI is there, you can remove the UI after you've estimated the UI in the usual way. The UIs are the excesses in the dependent variable. That cannot be explained by the independent variable. We know that. Also note that when the fixed effect model, the estimator becomes the best, blue, only when the sample size is large. So when you're doing this kind of things, you've got to have a bigger sample size. You have a smaller sample size, it will punish you. You still go and estimate the 10, and the 10 will still be showing that nothing is significant. So let's go back to the original data. This is original data. Let's convert it to the new one. So this is the new one. This is the one you got to tell people when you are estimating the model load. You have to write them and specify the model. This is a generalized version of the fixed effect model, but this specific model is when you bring the actual education experience into the thing. Let's do that. So you can see that in the specification, we have removed the fixed variables and we have incorporated the changing variables. And you will notice that this is similar to the first difference approach. The only thing is that this one has totally removed the unobserved thing. So how do we estimate the model? Well, we have wiped out all the fixed factors. We have allowed all the varying factors. We had dropped experience, even though experience was changing, but it was changing deterministically. So we dropped it in the fixed. Okay, and we have seen that experience square is here. Why? We said it before that when we include a full set of year dummies, but the first, we cannot estimate the effect of any independent variable whose change across time is fixed. With experience, every worker works every year, so experience always rises by 1, but it rises deterministically for everyone, and that makes experience constant over time. When you run the model and you add experience, it will not work because it detects it, that it's assumed by the PLM to be perfectly correlated with experience squared. And fixed effect can easily be computed using the pooled OLS based on the time demeaned variable. We said all this already. So let's now run the fixed effect model. Let's run the fixed effect model. Okay, so all of these models are fixed effects, but watch the way I've renamed them. Some of them they're all having within. Look at it, there are 3 of them. But the thing is that when it comes to the effects, the individual specific effects and the time, you can run the model where the effect is focused on individual or on time or on 2 of them. So that's what I have here. Okay. Individual, time, or 2 of them. You can choose whichever one. Okay. So I'm going to take that and I'm going to run it in the R, then we see the results. Okay. All the others are here, don't worry. So let's go to the one I said it was this, so we'll not run it. That is so much, it deals with only factors.
Okay.
So I don't even want to do that. And let's look at the one that is individual. This is the same fixed effect, but with individual. The focus is on the individual. This is the results. It gives you some very good results.
Wow.
But it also omits some variables, which is okay. Then the one with the time, which is time specific, that is this. That one, everything that is fixed is removed, as you can see.
Yes.
So even the time dummies are removed, and all of it is significant.
Yes.
Then the one that is two-way, that one is both the individual and the time. The 2 ways, again, it omits the time. And the reason why it omits the time is because you are saying 2 ways. So to try to pick any one of them, and that one is not fully significant for marriage.
Yeah, for marriage.
So which is the best one? Well, the best one is this. This one, the one we did before. Okay. And that is the normal fixed effect model, which we just said within, we didn't indicate even whether it has time effect, individual effect, or 2-way effect.
Okay.
That one shows Some very, very significant results. But of course, you will notice that the way you interpret the coefficient is also important. In fact, look at even the estimate of the time
dummies.
The time dummies. It goes to show that because of the inclusion of other factors, the effect of time on wage wasn't felt.
Yeah, that's decreased.
When you excluded some fixed factors, the effect of time on wage are highly felt. You know. And in practice, this can be true because when certain things are there, sometimes certain regulations are there. And these regulations make it difficult for you to see a positive effect of time on your wage. Because, for example, if somebody sends product from the US to Africa, and because those things are, because of the regulation, tariffs, VAT, e-levy, and all of those things, it makes it difficult for a person to see whether this product is even valuable to him. Meanwhile, it's so valuable to him, but now the person doesn't even want to buy the product again because of external conditions. I don't know if you guys get what I mean.
Please come again.
So if you are trying to buy iPhone 16,
okay,
iPhone 16 is easily buyable, maybe in the foreign land. When it comes to your local land, people don't want to buy it because they feel it's too much. But the fact that it's too much is not the fault of the manufacturer. It's a fault of your fixed regulation.
Yeah.
You get what I mean?
Yes,
so your fixed regulation is making it difficult for people to recognize this thing.
That's true.
And that's what you see. So now when we remove those fixed factors like ethnicity, like experience, like those other things, now we are seeing the real effect of time on the wage. You can see that the percentage changes are looking good. That's what I'm saying.
Okay.
That's what I'm saying. Okay. All right. So that is fixed effect model. That's the best model so far. So far. Now remember that the other ones you are not able to interpret. It is part of the model. So even though you can't see ethnicity and interpret, it doesn't matter. It doesn't matter. What matters is that you got a model. And we are going to finally check which model is the best anyway. It's a powerful test.
But really, does it not matter? Because many times in doing your research, you really want to see how some specific predictors affect the response. So, like say you're concerned about education, you're concerned about experience.
Good.
But this one are taken out.
So in this case, what you will do is that when you want to now interpret those specific predictors, you will go and use a model that actually incorporated them. Only for those predictors, not for everything in that model. I don't know if
however, you've already downgraded that model of a sort.
Yes, you've downgraded the model, but you need those variables.
Exactly.
Yes. So if you need those variables, okay, the model is only downgraded. Remember, it's only downgraded in your choice model, isn't it?
Yes.
But your choice model doesn't incorporate the variables that you need.
Exactly.
So you go back to that model, and only for the variables you need, you check their significance.
Okay.
Only for those variables. That's why you remember that when people are interpreting they bring all the models in the journal paper.
Yes.
They don't just say that because I've chosen this one, I'm throwing this one away. When you read the analysis carefully, they will indicate some of these points to let you know that, oh yes, we are using the fixed effect model, But, you know, for the purpose of the interpreter, remember that using the pooled OLS, experience has a positive effect on wage, because you don't have that in the fixed effect one. So they are using the pooled. That's why they would have also brought all the other models.
Okay.
All right. So this is a fixed.
Okay.
Go ahead.
Many times a change in eliminating one variable drastically changes the coefficients for all the variables.
Oh, not necessarily. I get what you mean.
Okay.
That is also why, if you like, you can remove the variables one by one and see whether the others change significantly.
Okay.
You see, it's not usually the case at all.
Okay. Okay.
All right. This is a balanced model. Note that at the top.
Yes.
The last time I said it wasn't balanced, one of you said that it was mine that wasn't balanced.
Yes, mine was balanced.
Okay. Now, fixed effect model can still have issues. So, issues of heteroscedasticity and autocorrelation, you have to still check them. And so you can download the LM test package and run the model with the, you know, with a white text, the white robust text. Sometimes it's called Huber white standard errors, to check for possible situation. Let's do that and see. Like, you want to take care of all possibility. That's the whole thing. So after the LM, you run this. What is that? And this is it. If you run it with this, is that different from the previous one? Let's see. It's the same thing, right?
Yes, like it looks like the same thing.
Yeah, it's the same thing. So we run with the cluster robust, is the same thing. But remember the last one we did, I told you that the new OLS is a very fine one. You remember?
Yes, Doc.
So let's run it to see whether with the new OLS. So you go to, this is after you run the fixed effect. See this one, I'm calling it WNWFE. That is a fixed effect, but with new OLS.
Doc, are you showing the Excel? We are still seeing the PDF.
Oh, sorry. The R. Let me know if you see it now.
Okay.
Yes.
All right, so let me go back, because I said that after running this LM, you run this the fixed with the Huber West, a robust Huber West. And this was original. This was the original one here. And it wasn't different from this one here. Okay, they were the same. So now we are going to run the newer West, okay, which is a function for estimating the robust covariance matrix of the parameters. Let's run that and see. And then see the estimate. You can see the big difference there.
Yeah, all significance now.
Okay, so it shows a clear significant value. You will use the Neumann interpretation to interpret your everything.
Okay.
And you can see that fixed effect with robust standard errors with newer West is the very best so far we've had. That newer West solves for both the heteroscedasticity and autocorrelation consistent covariance matrix estimation. So it solves for multiple problems in there. And note something, it is for a panel model. It is also sometimes, according to some guys called Driscoll and Cray method. So this newer West combines the methods of Driscoll and Cray, which is consistent with cross-sectional correlation, serial correlation, and several other heteroscedasticity issues. It's the best so far. But it has issues though. It has issues. Let me show you some of the issues with this fixed effect model. One of the issues of the fixed effect model is that it drops all the fixed factors. You remember that?
Yeah.
Yes, Doc.
The factors that don't change across time, and then it keeps only those that are changing. So how do you compare the fixed difference with a fixed effect? The thing we are saying that it drops because the model was designed for it to drop. So as for that, don't ask me. That's why when you spoke about the other one, I told you that if you want to handle those fixed factors, then you go and use those particular other models that brought them. Well, if you want to compare the fixed effect with the phase difference, when you are dealing with the same two time periods, because of the lag nature, okay, because they are all fixed and this one is fixed, the fixed effect, then you will notice that the phase difference and the fixed effect will be the same. But when the time periods are more than three or more, then they are not the same because phase effect focuses on just the one lag, phase difference focuses on all lags. So which one do you choose? Well, there's a video you can check later about which one is better. But we would have a test to prove which one is better very soon. The last model is a random effect model. Random effect model. The random effect model assumes that the individual specific effects are independently and identically distributed. Okay. In other words, they are on their own and they are not correlated with the dependent variable. See, it already assumes that they are not correlated. Okay. It does assumption there. It already assumes they are not correlated. It assumes that they are not correlated. If you look at the correlation is here, we've talked about this correlation a lot. So you can safely add them to the compose error. You see, you can have the compose error and have the UI in the compose error. Remember the fixed effect was trying to remove it from the compose error, but random effect will keep it in the compose because random effect says, forget it. They are not, correlated. All right. So it removes, we've said it, I've said it already, that the fixed effect removes it and treats it as a constant. So how does the random effect work? If we assume that there is no correlation between the UI and then the XI, then we will not need the fixed effect or the phase difference because they won't be any endogeneity. Because remember, the endogeneity is when the UI and the X are correlated. But then if the UI and the X are not correlated, then there is no endogeneity. So if there's no endogeneity, there's no fixed difference, there's no phase difference, there's no fixed effect.
Yeah.
Okay.
So if you use OLS, then you're going to get autocorrelation of the errors. That is why the random effect is very powerful here. Random effect is just like the feasible GLS that we did some time ago under cross section, if you can remember.
Yes.
Just that it is now on the panel, not on a cross section. So basically, random effect is feasible GLS on the panel. And it assumes that there is no what? There is no correlation between the error and that. The standard error here means that the covariance of the two errors, that is individual and then the noisy time, is 0. But then they are different across different times. The variances are the same if the two time periods are different. But if the two time periods are the same, then the variances are different. That's what this point is actually saying. The serial correlation, the autocorrelation can be handled by feasible GLS. We said it before, which assumes the name of a random effect. So let's look at the general model. There's a general model. We've been using this many times. The general model becomes this. You see, we have included the UI in the entire compose, the blue section. We've included everything. And then we've commented that the epsilon is IID with a 0 mean and a constant variance, not just a noisy one, but even the individual specific effect as well. I have a paper here you can check that uses this model, the effects and the random effect. Now let's check whether the random effect is efficient. If you correct for the serial correlation, the random effect is efficient. So you see, serial correlation can also still be present. If you correct for it, it can be efficient than the pooled OLS, all of them, which is great. So all we got to do is to correct for what? The serial correlation. If we write the equation for the transformed random estimator, okay, so this is the normal one, but we are transforming it by introducing a theta. And then we subtract that same mean, okay, based on the time, like we did before, we subtract it, but we multiply that by theta. Okay, we'll get all of these terms that you see here. We don't know what the theta is yet, but we know that if it is 0, we get back our original model. And you can see it here. If theta is 0 here, everything will fall back to the general model.
Yes.
Okay. And that way, the random effect now becomes OLS, because that thing, when it falls back here, that is a pooled OLS or the OLS. But if theta is 1, then the random effect will be equal to the fixed effect. Because if theta is 1, then theta times this yi bar would be yi bar. So that is fixed effect, if you can remember. So it just goes to tell you that theta is going to hover between 0 and 1. Because the random effect is not going to be OLS, neither is it going to be fixed effect.
Right.
The fact that it's random means that it's dancing. It's dancing between something and something. What then is theta? Theta tells you the percentage variability that comes from the error terms. Now, when I say error terms, I'm talking about the individual specific effect and the actual noise. There is a certain, like you are telling me that there is a chunk of error, but some of the error are coming from individual latent factor you don't see. Some of them are also coming from noise. Okay, now let's talk about the difference between. Now, one of them is what you don't see but you like. Another is also what you don't see but you don't like. So let's take something like an unmeasured ability of an individual, which is powerful. The person is very powerful in computer programming. He's able to do some great things in the company. You don't see it, but it's helping the person's experience to be very beautiful in the company. You don't see it, but it's helping the company. So it's good. That is a UI. But there's another latent factor. Maybe somebody is stealing money in the company. You don't see it, but it's affecting the company. That is noise. Are you guys with me?
Yes.
Yes, Doc.
So they are all, yeah. Now, what is the percentage of each that you don't see? Which one would you want to be more? The UI or the epsilon IT?
The UI.
Your guess is as good as mine. Okay. Now, we've seen that if the UI is 0, if the theta is 0, okay, then we fall back to the OLS. We said it before. And if it is 1, we fall back to this. So what you want to do is how do you do the two-step random effect estimation now? You have to find the variances to get the theta, which we don't know. Okay? And you do that by using the pooled OLS or the fixed effect. Then substitute that theta and use the pooled OLS on the transformed model you have. And then you can get back your theta. Certain assumptions here. We don't have a problem of endogeneity again, which is good. Okay? We have a random cross-sectional sample. You can replicate it. Strict endogeneity is there. No perfect collinearity. All the others, they are there. They also assume this, okay? Except the first one, which is a very powerful, good thing for the random effect model. The issue about no endogeneity is a big deal for that. So which one do you go for? In real life, in the application, you have to do both. Okay? Both of them are informative. Okay? You have to compute all of these models, compare all of them to determine the nature of the biases caused by each one by leaving the other one and all of that. Check which one has unobserved heterogeneity and then which one has errors and everything. You basically run everything. Empirical researchers, they decide on the fixed effect versus random effect based on whether the individual specific effects are correctly viewed as parameters to estimate the random. Now, if you look at such considerations, it's not correct. Because if you want to know whether we should use fixed effect or random effect, the best is to assume that the individual specific factor, the UI, is not correlated with the error term. That's the main thing. So in order for you not to run into that problem, what you do is that anytime you estimate fixed effect or random effect to handle heteroscedasticity and autocorrelation. Okay. It doesn't stop anything. Just going ahead to incorporate that is just another code to incorporate that, and then you handle it, and then you don't run into any problem. So let's go finally to our old model. This becomes the random effect model. Nothing changes. Everything is grouped into the blue term. And now we can specify our model finally. Remember I told you that under the random effect, everything is put in there.
Yes.
Everything. You can see the specification. Everything is there. Everything. Because you are assuming that the individual specific effect is not correlated with the error term. It's not correlated. So it's not correlated. There's no relation. There's no dependency. So everything, put it there. Everything, put it there. Everything, put it there. Easy to do that. So let's go and run the random effect. And all you got to do here is that under the section of model, you change that model to random instead of to within for fixed effect, instead of to pooling for pooled OLS, you know, and all the other ones. So let's do that in the R here. So I go to the R, I run my random effect model, which I'm about to do. Boom, and this is the results. Don't just look at the significance and say that because of the significance, we don't want it. I know Emily will choose it. You say that. Because that one is usually quick thing that people want to say. Oh, because of the fact that there are no significant distance. That's what we're going. No, there are so many things you can check. What we are seeing here is what we are seeing here. When we run this model, we also show the results in the model. So every model will show the results. Now, what do we see in the result? What does the result tell us? What can we handle? What can we solve? What can we make? This is the one-way effect, random effect model. It uses something known as Swami Arora's transformation. That is what has been estimated there. Let's look at the first part of the model because it's very interesting. The first part of the model tells you that it's a balanced model. That's good. The second part of the model tells you what effect you are dealing with. It tells you about two effects, the noise, the actual noise, and the individual specific effect. The two of them, they are there. Their variances are there, their standard deviations are there, and their shares are there. I'm telling you, these are powerful points. The theta is also there, 64%. That is a significant point we are going to talk about very soon. Now, what do they mean? Well, at the top of the table, you have the effect. In there, you see the idiosyncratic error. Okay? This thing we found it earlier, okay, which is the normal noise, and then the individual specific factor, the variances. And especially, you also see the theta, like I said. For a balanced data, this is a constant thing. You're going to have it all the time. For an unbalanced data, a summary of the values is also presented in the header of the output. So unbalanced data will give you something more. What does a theta mean? The theta measures the percentage variation that comes from the individual factor versus the noise. In other words, the variance of the random estimation. So let me tell you, in short, what is the damage from the noise percentage-wise, and what is the damage from the UI percentage-wise? You get it? That's what the theta is trying to do. What is the percentage variability? In actual fact, we don't know what the theta is, even though we know it's between 0 and 1. If it is 0, it's put OLS. If it is 1, it's fixed effect. But in practice, we don't know, but we can estimate it. It's just like beta parameter, we don't know, we estimate it. Okay. In here, in this example, most of the variation comes from the theta, the unobserved worker-specific effect, 64%. In other words, you remember I asked you which one is good, whether it's coming from the error or it's coming from the UI. Do you remember?
Yes.
Yes, Doc.
And you said it's good when it's coming from the UI, isn't it?
Yes.
Here, it is coming from the UI. So that's a good thing because it gives us an understanding why the random effect will always lie closer to the fixed effect than the pseudo OLS. Because remember that we said that when the theta is getting to 1, then we are moving towards fixed effect, isn't it?
Yes.
And when it is exactly 1, then purely is fixed effect. But you want that fixed effect because fixed effect has got more advantages than the pseudo OLS. So this very example, because the UI is more than that of the epsilon, we are now moving towards fixed effect than towards random, towards pseudo OLS.
Yes.
Okay. And you will see that this is a very good thing. So what does the 64 mean? Okay. Well, it means that 0.64 times the individual mean has been subtracted from the original data. And a large percentage of the total variation is attributable to the error. But the good thing is that the error is attributable to is the UI and not the noise. In this case, it's attributable to the UI error, not the epsilon I error in this case. And that conclusion here is very important, that in practice, the estimate is neither 0 nor 1. So it's in between. So this is a full data set. Okay. Now, once again, like we did before, you can run the random effect and add other things, just like we did for the fixed effect. There's a random effect model and then random effect method. So there are different methods of the random effect. If you run the model, then you can run a different method. One of the methods is a Mamiya method. Another is Warhus method. Okay. There is a Nelov method. And then several other things that one can actually do. Okay. So all of these are different kinds of methods that one can. You can also introduce the effects into some of them if you want to introduce the effect into some of them. Okay, let me go back here and show you all of these methods. We are not going to look at which model to finally choose. We'll look at that next time. But look here. So all of the methods, you can run them. Okay, and I've actually.
Doc, are you showing the R?
Oh, yeah. Sorry, let me just go. All of the methods here.
Okay.
You can see that?
Yes.
Okay. It looks like, well, I didn't run these ones, so I'm going to just run them. Yeah, because there were so many, so I decided not to bother myself. But it's always nice to run some of them. So I'm just going to run one of them. This one. I'm going to just run the Amamiya method. There you go. You see that it's not looking too good.
Yes.
But that is only for the time dummies. Most of the time. The time dummies. But in any case, you have run the method. You have run the method, but please, if it's not looking too good, doesn't mean that that's the model you are not going to use. You'll be surprised that when you go and do the test as to which model to select, they will tell you that this is the model to select. Because sometimes you can use a bad model that will be giving you significant results, when in fact you are not supposed to have significant results. You know that?
Yeah.
Yes, okay.
The thing must not be significant, but you are forcing it to be significant. My professor said that instead of looking at why they are not significant, you are forcing it to be significant. So sometimes you have to, but you can do that of the rest. Okay, this was the first one. The second one was a Walhus method. Okay, this is the Walhus method here. If I run that, this becomes the result. Again, it appears that this one is slightly better than the one before in terms of significance.
The last two, yeah.
Yes. Then there is another one, which is the Nelov method. Nelov method, something like this. If I run that, that one takes you back to the previous one. And like I said, there's a last one you can run, and incorporate the effects. The effects that we used to have. Okay. Incorporate this effect and see. That's it. Doesn't give you much most of the time, this effect. So you can run these models and eventually put it all together. Now, the next thing is, which models should we use? Which models should we, before we create a table for all? That will be done next time. We will now finally decide on which model to select. But now, today was just to know the models that are available to be used. These are all static panel models, not dynamic panel models. Okay. So look at that, and then we'll finally go to dynamic panel. Great.